Alright guys, I wanted to show you some examples. Don't get overwhelmed. I'm going to show you a lot of examples. Memorize nothing. Think about everything. Look for patterns. Show you some examples of three different types of equations and how they can be written, why they could possibly be useful to write it through different ways for a small selection of reactions. Here's a reaction where silver nitrate reacts with sodium chloride to give silver chloride, solid, precipitate, and sodium nitrate. The molecular equation is written like this, so I just have one silver nitrate entity, species, in solution, one sodium chloride in solution, to give one silver chloride in solution. No, not in solution, that's a solid. What am I saying? Solid silver chloride precipitates out of the water, and so that's why you see a reaction happening, but the sodium nitrate stays floating in the water as well. This might be useful if I was looking to know it's a 1-to-1 to 1-to-1 ratio and doing some kind of stoichiometry or titration. It's also good to think about what's happening to with the ions that are reacting are the silver ions being positive and the chloride ions being negative, attracting each other so strongly that they form nice neat little crystals of chloride silver, chloride silver, chloride silver, chloride silver, chloride silver, chloride silver, on and on and on, hundreds and millions in 3 dimensions to form a little wet clumpy thing of silver chloride that sinks to the bottom of the water. That's a solid, that's aqueous, that's aqueous. I wonder why I didn't mention the nitrate and why I didn't mention the sodium. I wonder why. Oh, I remember why. Because they're called spectators. They don't really do anything. So the total ionic equation, as opposed to the molecular equation, lists all the ions in the water. So we have these ions in one beaker, these ions in another beaker. When they're mixed and mingled, we see the silver chloride solid form, but the sodium and the nitrate still float in the water. So you know what? There's this thing we do with total ionic equations. Number one, we rarely write them because they're so long, but when I'm first learning about the whole topic, I might write them all out. The reason why I don't want to write them all out is, isn't the sodium plus ion on this side exactly the same as the sodium plus ion on this side? Isn't the nitrate minus, single minus ion on this side exactly the same as the nitrate, single minus aqueous on this side? The answers are yes. So this one on the left of the arrow cancels this one on the right of the arrow. This one on the right of the arrow cancels this one left on the arrow. And lo and behold, all I have left is what we call the net ionic equation. The net ionic equation only lists the species that are interacting. So spectators be gone, and the silver ion in one beaker of water mixed with the chloride ion in another beaker of water produce silver chloride solid. Indeed, that is how you could make some silver chloride via precipitation. Alright, buckle your seat belts, but don't freak out. Here's a whole bunch of other examples. This one has potassium iodide reacting with lead nitrate. Looks like it's a 2-to-1 ratio, and I get lead iodide and 2 potassium nitrates. But wait a minute, what if I wanted to write all the ions out? 2 potassiums, 2 iodides, 1 lead, 2 plus, 2 nitrate, single minuses. Lead iodide solid, that's not aqueous, it's not an ion, so it's written together as a solid. And here I have potassium ion and nitrate ion. But wait a minute, doesn't this potassium and this potassium look exactly the same? And there's 2 on each side, and there's 2 nitrates on this side and 2 nitrates on this side. So I think the nitrates cancel. Cha-ching, cha-ching, I didn't draw these. And the potassium ions, 2 of them on this side, cancel 2 of them on this side. And I'm left with the net ionic equation in black here. That's simple. That's nice because it's only focusing on the species, the ions, whatever that are interacting, sort of ignoring and simplifying, ignoring the spectators, nitrate and potassium, and simplifying what we need to write, what we need to talk about. Although we often do use molecular formulas or molecular equations if we're talking about stoichiometry and titrations. That's when they're handy. Lithium hydroxide, aqueous, iron chloride, aqueous. This dissolves in the water, this dissolves in the water. I put lithium hydroxide in one beaker, of water, iron chloride in another beaker of water. You mix them together. According to this, I see iron hydroxide solid precipitate out of the beaker. But lo and behold, lo and behold, oh yeah, the lithium, 3 lithium ions in the water before and in the water after, 3 chloride ions. These 3 chloride ions, these 3 lithium ions are right here, and 3 lithium ions here, and 3 chloride ions here. Nothing changes with them, so all I write is, for the net ionic, 1 iron 3 plus reacts with 3 hydroxides to give 1 unit of iron hydroxide. Solid, precipitate. Oh, let's see, another kind of a, here's kind of a weird one. It's an acid-base reaction. Whenever I can form water or any other molecule actually in a reaction, that wants to happen. Water wants to form. It's very stable. Many molecules like to form because they're very stable, low in energy. So if I have an acid here, vinegar, with base, hydroxide, KOH, this H will join up with that OH to make HOH. Sometimes I write water HOH to emphasize where it came from. It came from an acid-base reaction. So this now looks nothing like this and this, or I could write it, I could say, yes, potassium hydroxide is a strong base, so the potassium comes apart, and that's the only spectator. But this is a weak acid, and it's mostly not dissociated. It didn't come apart very much in the water, so we usually write that together, and the net ionic looks like this. Whew, interesting. I know, when you first hear about this, I cannot remember this. You're right, you're not supposed to remember it. And we're trying to look for patterns. Here's a strong acid. Strong acids come apart totally in water. Here's a weak base, but it's usually one way to write it, NH3 aqueous. Yeah, so what happens is the NH3 aqueous gains one of the H's from, or both of the H's from the sulfuric acid. And what are the spectators here? Sulfate. Oh yeah. So in any case, if we end up with 2 and 2 and 2 in the end, we just cancel the 2's or divide by the common term, common factor to simplify a little bit. That's the net ionic equation. That's a good one to think about. I've seen that one on tests before. It's so simple but so fundamental. This is a confusing one actually. Copper and nitric acid. If I were to write out the ions, copper, that's not an ion, that's a solid piece of copper. A silver ion, 2 silver ions, 2 nitrate ions, 2 nitrate ions, 1 silver. Well, that's not so confusing. What am I complaining about there? Oh, I know. I was thinking about the copper and nitric acid reaction. Wonder if I have that one down here. Oh, yeah. You see the spectators, don't you? It's just the 2 nitrates here, 2 nitrates here. Fluorine gas bubbles through sodium chloride water, becomes sodium fluoride. The fluorine gas gains negative electrons from the chloride. Total ionic, net ionic. What are the spectators? 2 sodiums here, 2 sodiums here. That's about it. More? Lord, when will this end? What am I forming here? Oh, here I'm forming a molecule of NH3 as opposed to the ion of ammonium, NH4+. So forming a molecule likes to happen. So the spectator here looks like 2 lithiums and 2 lithiums. By the way, you're quite a ways out, not to belittle your skills and abilities, but you're quite a ways out from being able to do this easily and quickly. We wouldn't ask you to write each of these on a test per se just from scratch, but we might give you an equation like this and say, what kind of an equation is it? Molecular equation? Net ionic equation? No. What drives this reaction? Oh, the formation of a gas. H2S gas is a stinky, rotten egg gas. It's actually kind of poisonous. Not kind of poisonous, very poisonous. But our noses are so sensitive to it that as soon as we smell any, we run the other way. So, in any case, formation of molecules. So this molecule likes to form. It's a stable entity. And so hydrogen ion come together with the sulfide ion. The spectators look like potassium on both sides and chloride on both sides. You can thumb back through these, of course, on the PDF and ask me questions and think about how you don't care and how you'd rather be outside and having fun. I'm just kidding. But anyway, we're studying chemistry right now. Oh, this is a cool one. I'm a nerd, I know. Yeah, I form a water molecule, so that's one driving force. I also form another solid precipitate called barium sulfate. That's a driving force. So what are the spectators in this total ionic equation? Which ions are exactly the same on the left and the right? Nothing. No spectators. Crazy. So sometimes the total ionic equation is the same as the net ionic equation, which doesn't seem to save you much time. But that's alright, I'm just saying. Copy and paste. Oh yeah, this is the last one. Is this the last one? This is the last one. This is the pain in the backside. The reaction of copper with nitric acid. A little confusing because the nitrate unusually disproportionates. Some of it breaks apart into the NO2 gas and water. In any case, if I were to give you the total ionic equation, look at it and see what cancels. I have 2 nitrates here and 4 nitrates here. The answer is 2 of these cancel with 2 of these. These all go away, but 2 are still left behind over here. Nothing else is actually a spectator, but those 2 nitrates, not all 4 nitrates, are spectators. Phew! Are you panicking yet? You shouldn't be. Just ask a good question. Thanks for watching, guys. Seriously. See you soon.